Started section 5.1 last time, and we're going to complete that section today. We're taking a look at complex numbers, and let me just give you a real quick recap of where we were and where we ended up. So complex numbers are numbers of the form a plus bi. I is an imaginary unit. It's equal to the square root of -1. And we talked about adding and subtracting. And adding and subtracting looks just like with polynomials, combined like terms, and so forth. Multiplying has this additional caveat that if we get an I squared, then we have to replace it with -1. Excuse me. Division doesn't look like things that we have done precisely in the word divide. It's more along the lines of getting a denominator that's in a rational form. And so we looked at things called complex conjugates. And so a conjugate of a complex number or a complex conjugate takes the a plus bi, makes it a minus bi, and it does it on purpose so that when we multiply, we end up getting the inside terms to cancel out. We also call this difference of squares when you're working in algebra, and we end up with the first term squared and the last term squared. There's no i's, and that works to eliminate the i's in denominators, but as a natural byproduct, that typically inserts i's, or at least doesn't get rid of i's in the numerator at the same time. So there's still i's in the problem, they're just not in the denominator. And we were taking a look, this is where we left off, with square roots. So when we talk about the square root of a negative number, what happens is that negative is understood to be a -1 underneath that radical, and the square root of -1 is I. So when we have a negative, we can kind of have the feeling that that negative comes out from underneath the radical as an I. That's kind of how we think about it. And so what we had taken a look at last time is a few examples, 2 of them I believe. This first one was square root of -64. The negative means I'm going to have an I. 64 square root is 8, so I get 8i. And then over here, it wasn't a perfect square root, so we actually had to factor the number 200. It factors into something that is a perfect square root, right? The 100 is a perfect square, so we can take the square root of it. And then the 2. So the 2 stays underneath. The square root of 100 is 10. So the 10 comes out, the I comes out, and we have square root of 2 left over. So we have 10 square root of 2i, or 10i square root of 2. And this is the one we left off on. Okay. So one of the things that I want to remind you is that when there's addition and subtraction underneath the radical, you can't just bypass that and take radicals of specific pieces. So I can't just say, okay, well, I've got a square root of a 5 squared here, and then I'm going to have a square root of the other part, right? I actually have to simplify what's underneath the radical first because of the addition and subtraction. So when we're taking a look at this one, 5 squared is 25, and that will be part of what I need, but I need to know what is 4 times 6 times 3. So somebody grab a calculator, multiply that out real quick. What do you get? It is 72, so this is minus 72. And then we need to know what 25 minus 72 is. -47. Now, the negative part of that will come out as an I, right? What about square root 47?
It's a perfect square. Or you can't do anything with it.
Yeah, so there's a different word, prime. There you go. It's prime. There isn't a perfect square that divides it. Even if there's a number that divides it, if it's not a perfect square, it kind of doesn't help us out. And 47 is prime. So this is actually I square root 47. So in some sense, this problem starts out looking a little bit messier than what we have had on the previous 2 problems. But in the end, because 47 ends up being a prime number and it doesn't actually end up dividing or simplifying and it's staying under there, it's easier at the end. So you kind of get a little bit of give and take on this particular one. All right, so a few more. These are actually showing 2 different square roots, and you've got subtraction in between them. So we're just going to deal with each of the square roots independently, and then if we're able to combine by subtracting the results, then we will be able to do that. So let's start out with the -81. So the negative comes out as an I. What is the square root of 81? Yeah, it's 9. So we actually know that one. It is a perfect square. It is 9i. Then there's a minus. Square root of 144 is 12, and then the negative underneath there comes out as an I, so this is 12i. And then 9i minus 12i is what? Yeah, -3i. So keep in mind, again, because these are separate square roots, we have to deal with them separately, and then we combine them. We can't just put them all underneath the same square root and deal with it that way. So in a very much the same way that this one, you can't separate them into square roots. These 2, you can't combine them underneath the square root. You have to deal with them as they're given to you and simplify them as you go, right? Not at the beginning and merge them into something different. All right. Oops, I skipped one. This one. Here we go. All right, so this one has -2 plus the square root of -11, and then it's squared. So I'm going to remind you of a fact that I will tell you. Some of you are going to still forget it. I've had Calc 3 students this semester who have done this error. Okay, you cannot distribute squares, right? So I can't just square the first piece and square the second piece because the whole thing is squared. That does not work. And I'm going to remind you again why. I always use the same example. If I had 3 squared and 4 squared, 3 squared is 9 and 4 squared is 16, right? This is 5 squared. Well, it's 25 and then 5 squared. Everybody good with that? Notice if I try to do this the other way, like 3 plus 4 squared like this, if I did this, that is not what I wanted to do. Let me change the way I wrote this. Let me do this again. This is how I wanted to start it. My apologies, so that it looked more like my original problem. All right, 3 plus 4 squared. I'll get to the other piece in a second. 3 plus 4 is 7. So this would be 7 squared, which is 49. If I tried to distribute it the way that I had written it originally, 3 squared plus 4, 3 squared plus 4 squared, that's when I would have gotten the 9 and the 16. This would have given me a 25. And 25 is not the same, obviously, as 49. So whether I have the square on the outside or whether I have the square on the individual pieces, I do not get the same thing. Matters where it is. So when I'm taking a look at this, when I see something that is a quantity, addition or subtraction squared, what I have to do is I have to actually write down that it's being multiplied by itself. Right, that's what squared really means. It means multiply something by itself. Well, in this case, I'm multiplying the entire thing underneath, or inside of, rather, the parentheses, times the entire thing inside the parentheses. So take the second, write it out. Make sure you don't forget those pieces that are going to be involved. Now what will I do? Distribute or FOIL, right? I'm going to actually find these pieces individually. So I'm going to multiply the first and the outer terms. So -2 times -2 is 4. And then -2 plus square root -11. Okay, so -2 square root -11. Everybody good with that? We'll clean those up in a little bit. And then the other piece is the same thing. You're right. So I've got to have this one right here. I've got another one right there, right? I have another -2 square root -11. And then the last piece will be different. So this is -2 square root -11. And what happens when I do, actually, let me write it down. Oh, whoa. I want to show you something. Just a second. Hold tight. They don't exactly cancel. Well, they do, but let me show you why. Okay, so is everybody okay with me writing it that way for just a second? Okay. I want to show you what happens in the last piece from 2 different perspectives so that you can see they match up no matter which way you think about them, okay? So that's why I was going to write it that way for the moment. Okay. Let's go from left to right and simplify. Okay. So I have -2 square root -11 and another -2 square root of -11. So what is that?
4.
Yeah. -4 square root -11. We still have to deal with the fact that there's a negative underneath the radical, which we will. This last piece, so what Isaiah was saying is correct. When I multiply a square by itself, or square root by itself, I eliminate the square root. This is -11, right? That's a true statement. I want you to see that it also works if I had simplified it first. So if I did, I think where I want to write this. Let's just write it over here since I've got some scrap work all over here anyway. If I do square root -11 and square root -11 like this, but I pull the I out, what happens when I multiply I times I? I get I squared, which is -1. And then the square root of 11 times the square root of 11 is 11. So whether we simplify it sort of at the beginning before we do the multiplication, which would be what this one looks like, or whether we don't simplify it and we multiply the square roots together, I'm still going to get -11. Okay, so there's 2 different ways to think about that, and both result in the right solution. They're both correct. So I just wanted you to see that that worked. All right, there is one more thing that I need to do. There is a square root negative 11 still happening here in the middle, right? So this negative needs to do what? Yeah, it needs to be written in front with as an I. Okay, so that's one thing. And then I've also got a negative 11 at the end and a positive 4 at the beginning that I'll consolidate. Can we do that on the same step? Y'all good with that? Okay, so the 4 at the beginning, the negative 11 at the end. What will that become? Negative 7. I'm going to write it at the front. And then I have a negative 4, and then the I will come out from underneath from the negative on the 11. And then I have the square root 11. And another version, remember, I'm going to keep reminding you just in case just in case my math lab fusses about this, is that you could also see this written as 4 square root of 11 and then I afterwards. Just make sure your I does not go underneath the radical because it should not be there. Okay, is that all right? Makes sense? Okay. So the next one is a division one, right? So this says perform the indicated operations, write the result in standard form. All right, so taking a look at this right now, what do you for sure know we're going to have to deal with? What was it? The negative underneath the radical, right? You may not know that there's anything else for sure that we need to do, but the negative underneath the radical we will deal with. So let's go ahead and do that one first because we sort of recognize that one right off the bat. So it would look like that, correct? Okay, now in the sense of is this simplified, the answer is still no. And there's another thing that you might recognize when you look at this. So looking at this, what else might you say? Oh, I need to deal with that. The 18. I can simplify square root of 18. Now it's not a perfect square, right? So I want to show you just in case you're looking at this and you're like, I don't remember how to simplify those radicals. It's just been a minute, okay? So if you're dealing with a number that's not a perfect square, what you can do is you can make like a factor tree. So let's just do that for a moment and just completely factor this puppy on out so we can remind ourselves what we're looking for, okay? Because not all the numbers are really straightforward and easy to deal with. Some of them are messier. Okay, so what will divide 18?
6 and 3.
Okay, 9 and 2 or 6 and 3. So we pick one. I'll go 6 and 3. 3 is prime. So I'm done with that extension of the tree. 6 is not. So 6 will divide into 2 and 3. So my prime factorization for the number 18 includes the number 2, the number 3, and the number 3 again. Is everybody good with that? Okay. So if you've broken it down into factors like this, okay, and it's not the only way to do it, but this one works for all cases, which makes it friendly in that regard. What you're looking for is you're looking for anything that's occurring in pairs. Okay, so I see in pairs right now the 3s. There's 2 3s underneath there, right? So what that means is when I have a pair of things underneath a radical, it can come out of the radical one time. Because in essence what you actually have is the square root of 3 squared and the square root of 2. Square root of 3 squared would be 3. Okay, and if you're not sure, think about what 3 squared is. 3 squared is 9. What's the square root of 9? 3. Okay, so you can think about it as a multiplied out version, or you can think about it as the square root and the square canceling. Either way, the 3 will come out. So back over here, I have negative 15. I have minus. I'm going to put my 3 in front of my I, and then I have a 2 still underneath the radical. Is everybody good so far? Now, we're supposed to be putting in this in A plus BI form. So what I'm going to do is I'm going to take, this is like a merged together fraction, and I'm going to break it apart into 2 fractions that have that same denominator, 33. Okay? That will separate it into the A form at the beginning and the BI form at the end. So we're going to rewrite this as negative 15 over 33 and minus, and then 3I square root 2 over 33. Now, in some problems, we would actually sort of be done here, with the exception of maybe rewriting the I after it instead if we wanted, right? But on this one, there's more to do. A little bit, anyway. What can you still do on this problem? Yeah, these fractions are not in simplified form. So if you take a look at the first one, what will 15 and 33 both divide by? 3. So 15 divided by 3 is what? 5. And then the 33 is 11. So this first fraction simplifies to negative 5 over 11, and those don't have anything in common. That is a version of this fraction that's simplified. How about the 3i and then 33 on bottom? Yeah, again, the 3. Now, these both happen to be simplifying by 3. That doesn't have to happen. We could have one of these simplified, the other one not. Or we could have them both being simplified, but in a different way. This one happens to both be simplified by dividing them by 3 on all the pieces, but that doesn't have to happen. Also remember when you're looking at things, so this is 1 and 11, when you're looking at this to simplify, the radical does not get involved in the simplification. What's underneath the radical is a standalone piece that does not get manipulated with the division piece that we're working with, okay? It doesn't get involved. So the second piece then is negative. Negative. I have an I and a square root 2 over 11. So this is one version of this. Another version that we could write this in that's more truly the way that the question is worded would be to have it written like that. Okay, again, I have zero care about whether you use one or the other, but I think that my math lab might care. So I'm making sure you're aware of it, okay? Any questions on that one? It's a little bit more involved than the others we've done. Okay, last one. All right, so this one's back to looking like a multiplication problem, yes? Yes, okay. So we're going to multiply these, but I would like us to deal with the I parts first. And I will show you why I'd like to deal with that by showing you the error that can occur if you don't. We'll do that second. So let's do it properly and correctly first, and then I'll show you the error that can happen second. All right, so when we have the negative underneath the radical, we can pull it out as an I, correct? Okay, so that's what I'm going to do first. So I'm going to write this as 3i square root 7 and 2i square root 8. I know I need to deal with the 8 still eventually, but first just the negatives. Everybody good? Okay, what we're going to do next then is we're going to multiply the pieces that can be multiplied. The way that this is written, there is no addition or subtraction present, correct? What that means is that everything is being multiplied from the left and to the right. And one of the properties that you know about numbers is that they are commutative, right? Your real number system and the complexes as well are commutative. Commutative means that the order in which we multiply doesn't matter. 3 times 2 is 2 times 3, right? We also know that multiplication is associative. Associative means that I can reorganize it. So if I have 2 times 3 times 5, I can multiply the 2 times 3 first or the 3 times 5 first, and it doesn't make any difference. I'm still going to get at the end the same answer, right? Okay, so what that tells me when I look at this particular problem is that it's perfectly legal, acceptable, correct to multiply the pieces that are easy to be combined. For example, it's easy to combine the 3 and the 2. 3 times 2 is 6. And it's easy to combine the I and the I. I times I is, I squared. We'll put it in as -1 in a minute, okay? And then the other two pieces that are left here are square roots. They're also easy to combine. They can actually go underneath the same radical. Now, that doesn't simplify things because I still have that 8 that I need to factor in a minute. But I can put the pieces that go together. So this isn't exactly a like term issue, but they are like pieces that I can combine. Everybody good so far? Okay, so it's already been mentioned that this I squared is equal to -1. So this at the beginning is really now a -6. And then I'm going to factor the 8. So let's do it again on the side, just as a reminder of how it works. 8 factors into what? 2 times 2 times 2. You could have written it as 2 times 4 as well and broken it down further. I'm looking for repeated values. I have a lot of them. They only repeat. There are 2 of them that are 2's underneath. So that means I've got 2 squared or 4 underneath, which means I can pull that out as a single 2. So there will be one of these, because of the way it breaks down, that'll get pulled out. So this -6 will have a 2 pulled out with it. And then the other 2 that did not get pulled out, this one right here, will stay underneath with the 7. Okay? So this says -6 times 2. We can do that. That's -12. And this says 7 times 2, which is 14, and this is our final answer. Okay? So there's a property for real numbers that says what we just did over there. It says if I have the square root of a and the square root of b, this is the square root of ab. That's a property I just used. This is a real number property. Here's the deal. If I do this wrong and I assume this property works for complex numbers, which it doesn't, I will get this problem incorrect. And I want to show you why it fails for those numbers by using this example, okay? So if I had done this problem from the get-go, where I'm combining the pieces, and I combine the two pieces on the outside, and I say, okay, I have 3 times 2, right? I'm going to combine those. And underneath the square root, I'm going to do the -7 and the -8. The 3 times 2 is 6, but what's going to happen underneath here? The negatives are going to cancel. Okay? So I'm just going to get 7 times 8. That's the same thing, right? I'm going to get 56 with 7. The negatives are going to cancel. Negative times negative is a positive. But that means that the rest of it, I can simplify the 2. This is the 8. It'll have the 2's, and I will end up getting 12 square root 14 here. But the negative won't be out there. And it won't be out there because I never got an I squared. And I never got an I squared because I never pulled out my I's. So I can't just say square root, merge them all underneath. I can only do that if there's positive values underneath the square root. Does that make sense? So please be careful. It's a really easy mistake to make. We can't simplify square roots and merge them together if there's negatives underneath there. All good? All right.